What if the first human to step through a wormhole isn't some distant descendant of ours, but someone alive today? Picture this: a shimmering tear in the fabric of space, a tunnel carved through the cosmos itself, and a lone traveler stepping into the unknown. The moment their foot touches the other side, everything we thought we knew about the universe changes forever. This isn't just science fiction. It's a possibility that some of the brightest minds in physics are racing to unravel. And the theories, they're wilder than anything Hollywood could dream up. From Einstein's equations to cutting-edge quantum experiments, the idea of wormholes has teased scientists for decades. But what if the first real wormhole journey isn't just a fluke of nature? What if it's something we create? Imagine unlocking a doorway to another star system, another galaxy, or even another time. The implications are staggering. Civilizations could meet before light itself has had time to travel between them. The cosmos would shrink in ways we can barely comprehend. And yet, buried in the math, hidden in the data, there are clues: 30 astonishing theories that could explain how it all begins. Some say the first wormhole might already exist, lurking in the heart of a black hole. Others believe we'll forge it ourselves, bending spacetime with energies beyond anything we've ever harnessed. There are even those who think the first travelers won't be human at all, but something else entirely. The questions pile up faster than the answers. How stable would a wormhole be? Where would it lead? And what happens if something comes back through? Today, we're diving into the most compelling, mind-bending ideas about how humanity, or something beyond humanity, might crack the universe's greatest shortcut. Strap in. By the end of this, the stars might feel closer than ever. The idea of a wormhole didn't spring from science fiction. It emerged from the pages of Albert Einstein's own equations. In 1935, Einstein and his colleague Nathan Rosen stumbled upon something extraordinary, a hidden shortcut in the fabric of spacetime. They called it an Einstein-Rosen Bridge, and on paper, it looked like a tunnel with two mouths connecting distant points in the universe. Imagine folding a piece of paper so two dots touch, then punching a hole through them. That's the essence of their discovery, a cosmic cheat code that defies distance. But here's the catch: Einstein and Rosen weren't actually thinking about interstellar travel. Their bridge was more of a mathematical curiosity, a quirk of general relativity. The equations suggested these tunnels could exist, but they'd be unstable, snapping shut the instant anything tried to cross. Picture stepping onto a rope bridge that dissolves beneath your feet. That's the problem physicists have wrestled with for nearly a century. The math allows for wormholes, but nature seems determined to keep them out of reach. Yet the dream didn't die. Later researchers realized something astonishing. If you could line the throat of a wormhole with exotic matter, a hypothetical substance with negative energy, it might stay open long enough to traverse. Think of it like cosmic duct tape propping the tunnel open against gravity's relentless pull. The numbers work, at least in theory, but exotic matter isn't something we can just scoop up. It's never been observed in nature, and creating it would demand energies beyond our current reach. So where does that leave us? The Einstein-Rosen Bridge remains a tantalizing maybe. It's the prototype, the first whisper of a possibility that the universe might allow shortcuts after all. And while we haven't found one yet, the very fact that relativity permits their existence keeps the door cracked open, just wide enough to let our imagination slip through. So if exotic matter is the key to holding a wormhole open, what exactly is this mysterious substance? Picture trying to build a tunnel through a mountain where the walls actively push outward instead of collapsing inward. That's the bizarre behavior of matter with negative energy. Unlike everything we encounter in daily life, this theoretical material would defy gravity's pull, exerting anti-gravitational pressure to keep a wormhole's throat from pinching shut. The numbers suggest it's possible, but here's the catch: no one has ever held a chunk of this stuff in their hands. the hunt for exotic matter isn't just wild speculation. Quantum mechanics hints at fleeting glimpses of negative energy through phenomena like the Casimir effect. Squeeze two ultra-smooth metal plates impossibly close together in a vacuum, and the space between them becomes a battleground for virtual particles. The result, a measurable force that acts against normal gravitational pull, a whisper of the physics we'd need to stabilize a wormhole. Laboratories have replicated this effect, but scaling it up to cosmic proportions is like trying to power a city with static electricity from a balloon. Some physicists propose shortcuts. What if we could cheat nature by engineering spacetime itself? Projects like the Alcubierre warp drive concept borrow similar principles, warping spacetime into bubbles that could theoretically move faster than light. While not a wormhole, the underlying math reveals a shared challenge. Both ideas demand energies comparable to converting entire planets into pure fuel. Even with futuristic tech, that's not exactly a practical road trip solution. Yet the most radical theories suggest we might not need to create exotic matter at all. Certain solutions in string theory posit that negative energy could exist naturally in higher dimensions, strands of cosmic geometry curled up tighter than atoms. If true, the universe might be hiding its own door-building materials in plain sight, woven into dimensions we can't yet perceive. Until we crack that code, wormholes remain tantalizingly out of reach, yes, but written across the cosmos in equations we're still learning to read. The strangest twist in the wormhole story might not come from the vast emptiness of space, but from the bizarre world of quantum physics. Imagine two particles so deeply connected that changing one instantly affects the other, no matter how far apart they are, a phenomenon called quantum entanglement. Einstein famously dismissed this as spooky action at a distance, but what if that spookiness isn't just some abstract quirk of quantum mechanics? What if entangled particles are literally linked through microscopic wormholes? This wild idea stems from a groundbreaking conjecture known as ER equals EPR, proposed by physicists Juan Maldacena and Leonard Susskind. The cryptic name combines two once separate concepts, Einstein-Rosen Bridges, those hypothetical spacetime tunnels, and the Einstein-Podolsky-Rosen paradox, which first described quantum entanglement. The stunning implication: every time particles become entangled, a tiny wormhole might form between them, weaving the fabric of spacetime itself into a hidden web of connections. Think of it like this: if two entangled electrons are cosmic twins sharing one existence, the ER equals EPR conjecture suggests they might be holding hands through a wormhole too small to see. These wouldn't be the Stargate-style tunnels of science fiction. They'd be Planck-scale structures narrower than an atom and vanishingly brief. But here's where it gets mind-bending. If true, this would mean the universe's most fundamental particles aren't just communicating faster than light. They're bypassing distance altogether through spacetime's backdoors. The implications ripple across physics. Black holes, notorious for swallowing information, might use these microscopic wormholes to preserve it, solving Stephen Hawking's famous paradox. Quantum computers, which rely on entanglement, could be inadvertently tapping into the universe's innate wormhole network, and if we could somehow stabilize or enlarge these fleeting tunnels. The dream of traversable wormholes might not start with massive engineering, but with mastering the quantum realm's hidden architecture. Of course, the ER equals EPR conjecture remains unproven, a daring hypothesis dancing at the edge of known physics. But if microscopic wormholes really do underpin entanglement, it would mean the universe has been quietly weaving shortcuts all along, not in the voids between stars, but in the fabric of reality itself, stitch by quantum stitch. But what if traversing a wormhole isn't about stepping through a door, but being violently ejected out the other side? Enter white holes, the cosmic antithesis of black holes. While black holes suck in everything that crosses their event horizon, white holes would theoretically spit matter out with unstoppable force, like a fire hose blasting material into space. Some physicists speculate that wormholes might not connect two black holes at all, but rather link a black hole's infinite hunger to a white hole's endless expulsion. This twist offers a chilling possibility. Wormhole travel could be a one-way trip. Imagine plunging into a black hole's crushing depths, only to be hurled out a white hole light years away with no chance of return. The math suggests these exotic exits might even birth new universes, their explosive outbursts becoming big bangs for pocket realities. It's a dizzying thought. Every white hole could be the starting gun for an entirely new cosmos, with our universe perhaps owing its own existence to some ancient wormhole's aftermath. Yet white holes remain purely theoretical. Unlike black holes whose gravitational shadows we've photographed, no observational evidence confirms their existence. Some argue they're mathematical mirages, solutions to Einstein's equations that nature simply rejects. Others propose we're looking in the wrong places. A white hole's violent output might mimic a quasar's brilliance or disguise itself as a gamma ray burst's fleeting flash. There's even a fringe idea that the Big Bang itself was a white hole event, the ultimate cosmic reboot. The implications unsettle our dreams of interstellar tourism. If wormholes chain black holes to white holes, they're less highways than catapults, flinging travelers across space without a return ticket. But here's the haunting question. If white holes really do create new universes, could every wormhole journey end not just in another place, but another time or another reality entirely? If wormholes can bridge distant points in space, could they also stitch together different moments in time? The unsettling answer lies in Einstein's own equations. According to general relativity, a wormhole with one end moving at near light speed while the other remains stationary would warp not just space but the flow of time itself. The faster-moving mouth would age slower due to time dilation, creating a mismatch between its clock and its stationary twin. Step through in one direction and you might emerge years before you left. Go the other way and you could leap centuries into the future. Suddenly, that cosmic shortcut becomes a time machine. But time travel through wormholes isn't just a matter of setting coordinates, it's a recipe for paradoxes. Take the infamous grandfather paradox. If you journey to the past and prevent your grandfather from meeting your grandmother, you'd never be born. But if you were never born, how could you have traveled back to alter events in the first place? This logical knot forces physicists to confront whether the universe would allow such contradictions. Some argue nature would conspire to stop you, a gun jamming, a missed train, some cosmic safeguard preventing the paradox. Others propose a darker solution. Every time-tampering act might spawn a parallel timeline, splitting reality into branches where both outcomes exist simultaneously. Then there's the bootstrap paradox, where an object or piece of information loops endlessly through time with no origin. Imagine handing Beethoven his own sheet music before he writes it. Where did the composition truly come from? Wormholes could transform history into a Möbius strip of cause and effect, where events no longer have clear beginnings. The math doesn't rule these scenarios out, but the consequences haunt our understanding of reality. If time travel via wormholes is possible, does that mean the future is already written? Or does every jump create ripples that reshape history? For now, these questions linger at the edge of theory and nightmare, a reminder that some doors, once opened, might not close so easily. The universe might be threaded with invisible cracks in space-time cosmic strings, relics from the Big Bang so dense that a single mile of one would outweigh an entire planet. These hypothetical flaws in the cosmic tapestry, narrower than an atom but stretching across galaxies, could be the universe's ultimate construction workers carving out wormholes where none existed before. Picture spacetime as a frozen lake. When temperatures drop, cracks form in the ice, imperfections locked in during the freezing process. cosmic strings may have formed similarly as the searing heat of the early universe gave way to cooler expansion. These cracks in reality wouldn't just sit there passively. Their incredible mass would warp space-time around them like a taut wire bending a bedsheet. Now imagine two such strings crossing or vibrating in just the right way. The gravitational forces at play could pinch space-time so violently that a tunnel forms between them, a wormhole stitched into existence by the universe's own primordial defects. The math is startlingly elegant. Unlike black hole-based wormholes that snap shut or require exotic matter, cosmic string wormholes might stabilize naturally through the string's unique properties. Their near-infinite density generates gravitational fields so intense they could counteract a wormhole's tendency to collapse. Some models even suggest these tunnels could remain open long enough for traversal without needing negative energy, solving one of the biggest hurdles in wormhole engineering. But there's a catch. Cosmic strings haven't been observed directly, though astronomers hunt for their fingerprints in the cosmic microwave background or gravitational waves. Even if they exist, manipulating them would demand technology beyond our wildest dreams. Imagine trying to pluck a guitar string thinner than a proton but longer than the Milky Way. The energies involved would dwarf anything our species has ever harnessed, yet the possibility lingers like a ghost in the equations. If cosmic strings are real, and if they can indeed birth wormholes, then the universe might be riddled with natural shortcuts woven into the fabric of reality during its fiery birth. We just need to learn how to find them, or more daunting still, how to pull the strings. When two black holes spiral toward collision, they don't just collapse into chaos, they might briefly stitch the fabric of spacetime into a tunnel. The violent dance of a merger warps gravity so intensely that simulations suggest something extraordinary could happen. For a split second, the black hole's event horizons might fuse into a throat-like structure, a wormhole suspended between them. It wouldn't last. The tunnel would either collapse or recoil into a new black hole, but for that fleeting moment, the universe could hold a portal where none existed before. This idea isn't pure speculation. When the LIGO Observatory detected gravitational waves from colliding black holes, the ripples in spacetime matched Einstein's predictions almost perfectly. But buried in the data were subtle anomalies, tiny deviations from what simulations expected. Some physicists propose these hiccups could hint at something stranger than two black holes merging. What if, in that final cataclysmic instant, a wormhole flickered into existence? The gravitational waves we observed might carry echoes of that tunnel's formation, like seismic tremors from a cavern briefly opening underground. Advanced simulations add fuel to the fire. When researchers model black hole mergers with certain exotic matter interactions, the equations occasionally spit out solutions where the merged object isn't just a larger black hole. It's a transient wormhole, a cosmic bridge that shudders and snaps under its own instability. The key difference: gravitational waves from a wormhole-forming merger would carry a distinct signature, a high-frequency echo following the main signal, like a bell's reverberation after the initial strike. Intriguingly, some LIGO detections have shown exactly these kinds of after ripples, though the evidence remains hotly debated. But here's the catch. Even if wormholes form during mergers, they'd likely exist for mere Planck time durations, far too brief for anything to traverse. The energies involved would tear apart atoms long before a traveler could reach the other side. And yet, the implications are staggering. If black hole collisions can birth wormholes, even ephemeral ones, it would mean the universe routinely weaves these shortcuts in the most violent events imaginable. Every time two black holes merge somewhere in the cosmos, spacetime might pinch itself into a tunnel, if only for a heartbeat. The next generation of gravitational wave detectors, like the planned LISA Space Observatory, could settle the debate. With sensitivity to lower frequencies, LISA might catch the whispers of a wormhole's birth, a sound no louder than a leaf falling in a hurricane, but one that could rewrite our understanding of cosmic connections. Until then, the idea lingers at the edge of physics that somewhere in the darkness, colliding monsters might be threading the needle of spacetime itself. What if every wormhole we've imagined is just a shadow, a three-dimensional projection of information scribbled onto the universe's edge? This is the spine-tingling idea at the heart of the holographic principle, a theory suggesting our reality might be like a cosmic movie screen, with everything we experience, including spacetime tunnels, encoded on a distant two-dimensional surface. It sounds like science fiction, but the math behind it is some of the most groundbreaking in modern physics. The holographic principle turns our intuition inside out. Think of a black hole. Normally, we'd assume anything falling in is lost forever, its information crushed into oblivion. But quantum mechanics insists information can't truly vanish. The holographic principle resolves this by proposing that all the data about what falls into a black hole isn't stored inside it. It's smeared across its event horizon like ink on a spherical parchment. Now stretch this idea to the entire universe. If a black hole's interior can be described entirely by its surface, why couldn't the cosmos work the same way? Our 3D reality, with its galaxies, stars, and hypothetical wormholes, might just be a rendering of data living on some unimaginably vast 2D boundary at the edge of, well, everything. This changes how we think about wormholes. If spacetime is a projection, then a tunnel through it wouldn't be a physical passage so much as a link between 2 points in the underlying code. Picture a DVD with a scratch that makes the movie skip, except here, the skip is a deliberate fold in the information connecting distant frames. The holographic wormhole wouldn't burrow through space. It would exploit the fact that space itself is an illusion, a layer atop deeper quantum entanglement. The most startling twist: this isn't pure abstraction. In 2014, physicists showed that certain wormhole solutions in anti-de Sitter space, a theoretical model of the universe, are mathematically equivalent to quantum entanglement on the boundary. Translation: when particles are entangled, their connection might literally be a wormhole in the hologram's geometry. It's as if the universe runs on a quantum computer, and wormholes are shortcuts in its processing code. Of course, there's a catch. The holographic principle works neatly in hypothetical universes with negative curvature, but ours appears flat. Still, even if the math isn't perfectly aligned yet, the idea reshapes the hunt for wormholes. Instead of searching for cosmic tunnels in the void, we might need to look for patterns in the quantum noise at reality's edges, an encryption we're only beginning to decipher. If this theory holds, the implications are staggering. A holographic wormhole wouldn't just bridge space, it might let us rewrite the rules of distance and connection altogether. The universe's ultimate shortcut could be waiting not in the stars, but in the quantum pixels of reality itself. Dark matter has long been the universe's most frustrating enigma, an invisible substance that outweighs all visible matter 5-to-1, yet refuses to interact with light or anything else we can easily detect. Its presence is felt only through gravity's pull, bending galaxies into shapes that shouldn't exist unless hidden mass is lurking in the shadows. But what if dark matter isn't just some exotic particle? What if it's threaded through space as a network of microscopic wormholes, stitching the cosmos together in ways we've barely begun to imagine? The math behind this idea is as elegant as it is radical. Galactic rotation curves, the way stars orbit a galaxy's center, reveal a mystery. Stars on the outskirts move far faster than they should based on the visible mass alone. Dark matter's gravitational pull neatly explains this, but its nature remains unknown. Now picture this: if countless tiny wormholes permeate galactic halos, their collective gravitational influence could mimic dark matter's effects. Each minuscule tunnel would warp spacetime around it, creating phantom gravity without any actual mass. It's like walking through a forest and feeling gusts of wind, not from the trees themselves, but from unseen gaps between them channeling invisible currents. Critics argue this hypothesis trades one mystery for another, but proponents point to startling possibilities. Wormholes woven into dark matter wouldn't just explain galactic rotation, they could solve the missing satellite problem, where fewer dwarf galaxies orbit the Milky Way than predicted. Traditional dark matter models suggest these small galaxies should be everywhere, but wormhole-structured dark matter might suppress their formation, smoothing out gravitational clumps that would otherwise birth them. The most provocative twist: if dark matter is a web of wormholes, it might not be entirely dark. Some models suggest these tunnels could emit faint gravitational waves as they vibrate, ripples in spacetime too subtle for current detectors but potentially within reach of next-generation observatories. Even more tantalizing, if such wormholes occasionally intersect or merge, they might produce bursts of high-frequency radiation, leaving fingerprints in cosmic background data. Of course, the idea remains speculative. Wormholes as dark matter would need to be incredibly stable, resisting collapse without exotic matter, a property no known physics can yet explain. Yet the allure persists. If true, we wouldn't just have found the universe's hidden scaffolding, we'd have stumbled upon its secret passageways, woven into the darkness we once thought was empty. The stuff holding galaxies together might not be particles at all, but the echoes of spacetime's own stitches pulling the cosmos tight from the inside. Beneath the smooth expanse of spacetime we perceive lies a hidden chaos, a seething, bubbling quantum foam where reality itself churns at scales a billion times smaller than an atom. This isn't poetic exaggeration, it's a prediction of quantum gravity, where the fabric of the universe isn't a tranquil sheet but a stormy ocean, constantly roiling with tiny wormholes that flicker in and out of existence like cosmic fireflies. These aren't the grand tunnels of sci-fi dreams, they're Planck-scale fluctuations, each lasting mere fractions of a second, stitching and unstitching the universe's seams in an endless dance. The idea traces back to physicist John Wheeler, who proposed in the 1950s that at unimaginably tiny scales, spacetime wouldn't be smooth but foamy, riddled with microscopic black holes and wormholes popping into being courtesy of quantum uncertainty. Picture a carbonated drink's fizz magnified to cosmic proportions. Each bubble is a fleeting wormhole, a shortcut through dimensions we can't perceive. The foam isn't static, it's dynamic, with tunnels forming, collapsing, and reconnecting in patterns so complex they'd make a beehive look orderly. But how could this quantum chaos ever matter to us? The answer lies in scaling. Most of these wormholes are vanishingly small, but some theories suggest they might merge or stretch under extreme conditions, like near the singularity of a black hole or in the searing heat of the early universe. Imagine blowing up a soap bubble. At first, it's tiny and fragile, but with the right conditions, it can expand into something vast. Similarly, a quantum foam wormhole caught in the right cosmic current might inflate, its throat widening from Planck scale to something traversable. The universe could be constantly seeding spacetime with these potential shortcuts, most doomed to collapse, but a rare few awaiting the perfect storm to stabilize. The kicker: we might already have evidence. The foam's turbulent nature could subtly alter light traveling across the cosmos, introducing tiny delays or scattering effects. Gamma-ray bursts, the most energetic explosions in the universe, have shown anomalies in their arrival times that some physicists attribute to spacetime's foamy texture. It's as if light passing through this quantum froth occasionally stumbles, tripping over microscopic wormholes we can't yet see. Yet the biggest question remains unanswered: could we ever harness this phenomenon? Stabilizing a quantum foam wormhole would require not just understanding gravity's quantum rules, but bending them to our will. Some speculate that advanced civilizations might have already cracked this code, using technologies we can't yet fathom to pluck a usable tunnel from the foam's chaos. Others argue nature itself might have done the heavy lifting, that somewhere in the universe a rare confluence of energy and geometry has already stretched one of these quantum whispers into a bridge. Until we unlock quantum gravity's secrets, the foam remains a tantalizing might be, But if Wheeler was right, then every cubic inch of empty space around us is a hive of potential wormholes, each a fleeting chance for the universe to rewrite the rules of distance and connection. The cosmic shortcuts we dream of might not be out there in the void. They could be right here, all around us, bubbling beneath the surface of reality itself. The universe is ancient, over 13 billion years old, which means intelligent life could have had a staggering head start on us. Picture a civilization not just a few thousand years ahead, but millions. What would their technology look like? Some scientists argue the answer might be written across our own skies. If advanced extraterrestrials exist, they've likely mastered spacetime itself, bending it into wormholes for interstellar travel. This wouldn't just solve the tyranny of distance, it could explain why we haven't found them yet. Consider Fermi's paradox. If the universe is so vast and old, why haven't we detected any aliens? Wormholes offer a chilling resolution. Advanced civilizations might not need to colonize star systems the way we imagine, spreading slowly across the galaxy. Instead, they could leapfrog between points instantaneously, leaving no trace of slower, light-based expansion. Their infrastructure wouldn't be Dyson spheres or generation ships, but a hidden network of cosmic shortcuts invisible to our telescopes. UFO sightings, often dismissed as misidentifications, might be fleeting glimpses of these transit points, like catching a subway train's flash as it vanishes into a tunnel. The idea gains eerie traction when you examine certain UFO reports. The Nimitz encounters in 2004, for instance, featured objects moving at hypersonic speeds with no visible propulsion, making abrupt 90-degree turns that defy known physics. Pilot testimonies describe craft appearing to fall like a leaf one moment, then accelerating to Mach 10, the next behavior that aligns disturbingly well with theoretical wormhole dynamics. If a craft could locally warp spacetime, creating microscopic wormholes to skip through air or water, it would explain the lack of sonic booms and the seemingly physics-defying maneuvers. But the most provocative twist lies in our own astrophysical anomalies. Fast radio bursts, powerful, unexplained cosmic signals have patterns that some researchers argue could be artificial. What if these aren't messages but energy signatures from wormhole stabilization? The power required to hold a traversable wormhole open would be colossal, potentially leaving detectable ripples across the electromagnetic spectrum. Even dark energy, the mysterious force accelerating the universe's expansion, might not be a natural phenomenon at all. Could it be the exhaust of unimaginable technologies, the side effect of countless civilizations stitching spacetime to their will? The sobering counterpoint is that if such civilizations exist, their motives might be forever beyond our grasp. A species capable of engineering wormholes could view us the way we view ants, interesting perhaps, but not worth contacting in any meaningful way. Or worse, their infrastructure might be so alien that we're literally blind to it, like microbes unaware of the internet's vast signals pulsing around them. Yet the possibility lingers like a candle in the cosmic dark. If we one day uncover proof of engineered wormholes, whether in anomalous gravitational waves, impossible stellar alignments, or even controlled lab experiments, it won't just revolutionize physics. It'll mean we're not alone in the universe, we're just very, very late to the party. Neutron stars are the universe's ultimate pressure cookers, stellar corpses so dense that a single teaspoon of their material would weigh 1 billion tons on Earth. Their cores, crushed under gravitational forces strong enough to warp atoms into spaghetti, might hide something even stranger, natural wormholes forged in the crucible of extreme physics. The idea stems from Einstein's field equations, which allow for spacetime tunnels under conditions so extreme they'd make a black hole look tame. But neutron stars don't just flirt with these conditions, they live in them. At the heart of a neutron star, matter stops behaving like anything we recognize. Protons and electrons are pulverized into a quantum soup of neutrons with densities rivaling atomic nuclei. Some theories suggest this environment could twist spacetime so severely that it pinches closed, forming a microscopic wormhole. Picture squeezing a water balloon until 2 points on its surface touch, except here, the balloon is reality itself, and the contact point is a tunnel to elsewhere. Unlike black hole wormholes, which might snap shut or require exotic matter, a neutron star's core could stabilize the passage through sheer pressure, like cosmic geology cementing a lava tube. The math gets wilder. Certain solutions in general relativity predict that if a neutron star spins fast enough, approaching a fraction of light speed, its rotation could twist spacetime into a helix, threading the wormhole like a needle through fabric. This isn't just theoretical whimsy. Pulsars, a type of rapidly spinning neutron star, have been observed with rotation periods as short as milliseconds. If one of these cosmic tops harbors a wormhole, it might leave fingerprints in the star's gravitational waves or X-ray emissions, subtle anomalies betraying a hidden tunnel's presence. But here's the catch: even if neutron star wormholes exist, reaching them would be a suicide mission. The surface gravity is 100 billion times Earth's. Tidal forces would shred any known material, and the radiation environment is lethal. Yet some physicists speculate that advanced civilizations might exploit these natural shortcuts by manipulating the star's magnetic fields or quantum states, turning a celestial corpse into a galactic transit hub without ever diving into the core. The most tantalizing clue might come from gravitational wave astronomy. When neutron stars collide, as observed in the landmark event GW 170817, their merger creates ripples in spacetime detectable across the cosmos. If a wormhole lurked in one of the stars, simulations suggest the gravitational wave signal would carry a unique echo, like a shout reverberating through a cave. Future detectors could catch this whisper, hinting that the universe's densest objects aren't just dead ends. They might be backdoors waiting to be unlocked. Until then, neutron stars remain cosmic enigmas. Their cores could be hiding the most stable wormholes in nature, forged in stellar collapse and spun into permanence by unimaginable forces. Or they might be gravity's final vaults, locking away spacetime's secrets behind walls no probe could breach. Either way, they remind us that the universe's most extreme places might also be its most generous, if only we could survive the trip. If the universe had a birth certificate, it might list wormholes as one of its earliest byproducts. Picture the Big Bang not as a single explosive event, but as a violent unraveling of spacetime itself. A moment when the laws of physics as we know them hadn't yet settled into place. In that seething cosmic froth where temperatures and pressures defied imagination, spacetime could have knotted itself into loops, forming wormholes as naturally as bubbles in boiling water. These wouldn't be the delicate tunnels we theorize today. They'd be primordial, rugged structures forged when reality was still malleable, threaded through the infant universe like scars in cooling glass. The math behind this idea is staggering. During the Planck epoch, the first fraction of a second after the Big Bang, quantum fluctuations operated at scales where gravity and the other fundamental forces were indistinguishable. In that chaotic soup, tiny wormholes might have spontaneously formed, some evaporating instantly while others stretched and stabilized as the universe expanded. Unlike wormholes created later, these relics wouldn't necessarily need exotic matter to stay open. The extreme conditions of the early cosmos could have frozen them into the fabric of spacetime like insects preserved in amber. If even a fraction survived to the present day, they could be lurking everywhere in interstellar space, within stars, even woven through the empty air around us. But how would we spot such ancient artifacts? Primordial wormholes wouldn't behave like sci-fi stargates. Many might be microscopic, their throats narrower than atoms. Others could have mouths disguised as black holes or masquerading as quantum fluctuations. The key to finding them might lie in their gravitational fingerprints. A stable wormhole from the Big Bang would warp spacetime differently than a black hole of the same mass, creating subtle distortions in the paths of passing light or unique ripples in gravitational wave detectors. Some models even suggest these relics could act as cosmic lenses, magnifying distant objects in ways that defy conventional astrophysics, the most tantalizing possibility. If primordial wormholes exist, they might connect not just distant places but different times. A tunnel forged in the universe's first moments could link our era directly to the dawn of creation, offering a window into conditions no telescope could ever peer back far enough to see. Imagine sending a probe through such a wormhole and receiving data from the quark-gluon plasma of the infant cosmos, or catching photons that haven't dimmed over 13 billion years. It's the ultimate time capsule built into the architecture of reality itself, yet the challenges are as immense as the rewards. A Big Bang wormhole surviving to the present would need to have navigated cosmic inflation, the universe's exponential expansion, without being stretched into oblivion. It would have had to dodge annihilation in the quark epoch, resist evaporation during the particle-anti-particle annihilation phase, and endure the violent clustering of matter into galaxies. The odds seem vanishingly small unless these tunnels are far more resilient than we think. Some theories propose they could be self-reinforcing, their throats lined with quantum fields left over from the early universe's phase transitions, acting like cosmic rebar in the fabric of spacetime. The hunt for these relics is already underway, albeit indirectly. When astronomers map the cosmic microwave background, the afterglow of the Big Bang, they're searching for anomalies that might hint at wormholes' presence. Tiny temperature variations or unexpected polarization patterns could betray regions where spacetime is threaded with hidden tunnels. Gravitational wave astronomy offers another avenue. If two merging black holes passed near a primordial wormhole, the resulting gravitational waves might carry faint echoes like sound bouncing down a hidden corridor. Perhaps the wildest implication is this: if wormholes from the Big Bang exist, the universe might be fundamentally interconnected in ways we've barely glimpsed. The vast cosmic web of galaxies could be stitched together by an invisible lattice of tunnels, a subway system built at the dawn of time. And if that's true, the greatest shortcuts through space and time might not be something we'll engineer in the future. They could be buried in our past, waiting for us to rediscover them. At the heart of our most successful physics theories lies a curious asymmetry. While electric charges come in positive and negative varieties, magnetism only ever appears as dipoles with inseparable north and south poles. But what if that's not the whole story? Grand unified theories, ambitious frameworks attempting to merge electromagnetism with the strong and weak nuclear forces predict the existence of magnetic monopoles, solitary north or south poles that could theoretically roam the cosmos like charged particles. These elusive entities aren't just exotic relics, they might be the missing ingredient for stable wormholes, turning mathematical curiosities into traversable gateways. The connection emerges from the peculiar properties of monopoles. Unlike ordinary matter, these particles would carry magnetic charge, distorting spacetime in ways that could counteract a wormhole's tendency to collapse. Picture trying to hold open a slinky. Normally it snaps shut, but if you thread it with rods that push outward, the coils stay apart. A monopole-lined wormhole might work similarly, with the particle's magnetic fields propping open the throat like cosmic scaffolding. The math is striking. Certain solutions in general relativity show that a dense enough concentration of monopoles could generate repulsive gravity, effectively battling the tunnel's natural collapse. This idea isn't pulled from thin air. In the hot, dense early universe, grand unified theories suggest monopoles should have formed copiously during cosmic symmetry breaking, a phase transition akin to ice crystals forming in cooling water. Most would have annihilated or diluted as the universe expanded, but a rare few could have survived, lurking in interstellar space or even trapped inside planetary cores. If any persist today, they wouldn't just be physics trophies, they'd be potential wormhole engineers' gold, The twist: monopoles have never been observed despite decades of searching. Particle colliders, ancient mineral deposits, even lunar rocks have turned up empty. Some theories propose they're simply too massive to produce in modern conditions, while others suggest they're hiding in higher dimensions or bound into invisible cosmic strings. But if they do exist, and if they're as powerful as predicted, a single monopole might carry enough magnetic charge to stabilize a wormhole large enough for transit. Here's where it gets speculative. Advanced civilizations, or even future humans, might not need to find natural monopoles. Quantum field theory suggests we could artificially create them by threading enough energy through a donut-shaped accelerator, essentially tearing spacetime's magnetic fabric to produce a synthetic pole. The energy requirements would dwarf anything achievable today, but the payoff could be immense. A single manufactured monopole might anchor an entire wormhole network, turning interstellar travel into a matter of engineering rather than generations-long voyages. Yet the most profound implication isn't technological, it's cosmological. If monopoles truly can stabilize wormholes, their scarcity might explain why the universe isn't crisscrossed with visible shortcuts. The rarity of these particles could be nature's way of keeping spacetime's tunnels carefully locked, reserving them for civilizations that crack the code of magnetic charge. Or perhaps the opposite is true. Maybe monopole wormhole hybrids are everywhere, disguised as dark matter or hidden in quantum foam, waiting for us to recognize the key that's been buried in our equations all along. The search continues. Next-generation detectors like the Mo-Edel experiment at CERN are hunting for monopoles with unprecedented sensitivity. If they succeed, it won't just fill a gap in particle physics. It might hand us the blueprint for spacetime's ultimate shortcut, written in the language of magnetic charge. Until then, the dream persists that somewhere in the universe's ledger of symmetries and broken rules lies a secret we've only begun to trace. A way to turn lonely magnetic poles into bridges across the stars. Our four-dimensional universe, three of space, one of time, might be just the surface of something far deeper. String theory, the leading candidate for a theory of everything, suggests reality could have as many as 10 or 11 dimensions, curled up so tightly we never perceive them. But what if those hidden dimensions aren't just mathematical abstractions? What if they're the key to unlocking stable wormholes, making interstellar travel not just possible but almost routine? The idea hinges on gravity's peculiar weakness compared to other forces. In our familiar four dimensions, gravity dilutes rapidly with distance, but in higher dimensions, its strength could fall off more slowly or even remain constant. A wormhole threading through these extra dimensions wouldn't face the same crushing gravitational forces that destabilize their four-dimensional cousins. Picture a tunnel dug through soft earth versus one bored through solid rock. The higher dimensional version might hold its shape effortlessly, its walls buttressed by geometry we can't see. String theorists have toyed with this possibility for decades. Certain solutions allow brains, short for membranes, to stretch across higher dimensions like sheets hung in a multidimensional clothesline. Wormholes could form where these brains intersect or warp, creating shortcuts between distant points. Unlike the fragile tunnels of four-dimensional spacetime, these higher dimensional passages might be naturally stable, requiring no exotic matter to prop them open. The energy to create them could even be within reach. Some models suggest particle colliders might one day produce microscopic versions, fleeting gateways to realms beyond our perception. The implications get stranger. If extra dimensions exist, a higher dimensional wormhole might not just bridge locations, it could connect entirely separate universes, each with their own physical laws. Our cosmos could be one bubble in a froth of multidimensional realities, and wormholes might be the threads stitching them together. Even more unsettling, traversing such a tunnel might not require moving through space at all. In higher dimensions, distance could be an illusion, 2 points touching directly through a fold we can't perceive. like ants on a crumpled sheet, unknowingly inches apart in the third dimension. Experimental clues are tantalizing but elusive. If higher dimensions exist, particle accelerators like the Large Hadron Collider might spot missing energy signatures of particles briefly slipping into other dimensions. Gravitational wave detectors could catch anomalies suggesting gravity leaking into extraspatial layers, and if a higher dimensional wormhole ever formed, even fleetingly, it might leave fingerprints in quantum entanglement patterns or cosmic ray data. Yet the biggest hurdle isn't evidence, it's imagination. Visualizing 10 dimensions is like explaining color to someone born blind. But if string theory is right, the universe's ultimate shortcuts might not be hidden in the voids between stars, but in the folds of reality we've yet to unfold. The higher dimensional wormhole isn't just a tunnel through space. It's a doorway to understanding how deeply the cosmos may be woven together in ways we're only beginning to trace. Time doesn't flow at the same rate everywhere, not even close. Near a black hole's event horizon, gravity warps time so severely that minutes for an observer could stretch into years for someone watching from afar. Now imagine that same time-bending chaos, but amplified at the throat of a wormhole. The result, a cosmic clock that ticks differently depending on which side of the tunnel you're standing on. Step through, and you might return to a universe where everyone you know has aged decades while you've barely blinked. This isn't just theoretical. Einstein's relativity guarantees that time dilation occurs wherever gravity is extreme, and a wormhole's entrance with its concentrated mass and energy would be no exception. Picture a traveler hovering near one mouth of the wormhole while their twin stays light years away. If the wormhole's throat is deep in a gravitational well, perhaps orbiting a neutron star or drifting near a black hole, time for the traveler would crawl compared to their twins. The deeper the gravity well, the starker the divide. A mission that feels like weeks for the crew could span centuries back home, turning interstellar exploration into a one-way trip through time. The real mind-bender comes when you factor in motion. If one end of the wormhole accelerates to near light speed, say, by slingshotting around a massive object, time dilation kicks in doubly. Special relativity dictates that velocity slows time, while general relativity says gravity does the same. Combine the two, and you've got a recipe for temporal whiplash. A traveler stepping through the accelerated end might emerge not just elsewhere in space, but centuries in the past or future. It's like a time machine built into the geometry of the tunnel itself, no DeLorean required. But here's where it gets eerie. Unlike classic time dilation scenarios where astronauts return to Earth older or younger than their peers, wormholes could create paradoxes that defy intuition. Open a wormhole, move one end, and you've created a closed time-like curve, a loop where cause and effect tangle into knots. Send a message through the tunnel, and it might arrive before you sent it. Step through, and you could meet your own future self, or worse, prevent your own birth. The universe hates paradoxes, which is why many physicists argue that quantum effects or unknown laws would prevent such scenarios. Yet the math allows it, whispering that wormholes might not just bend space, but the very arrow of time. The implications for exploration are staggering. A civilization that masters wormhole travel wouldn't just conquer distance, it would hold time in its hands. Colonies could be seeded millennia apart yet remain connected, cultures evolving separately yet never losing touch. Historians might walk among the subjects they study, and astronauts could return to worlds unrecognizable to those they left behind. But the price, every journey would be a gamble with time itself, where the safest path might be to never look back. The universe might already be running the ultimate quantum computer, not built with circuits or lasers, but woven into the fabric of spacetime itself. Imagine a wormhole not just as a tunnel through the cosmos, but as a processor, using the bizarre rules of quantum mechanics to perform calculations no silicon chip could ever match. This isn't just speculation. Some physicists argue that wormholes and quantum computers might be two sides of the same cosmic coin, performing the same impossible feats in radically different ways. At the heart of this idea is entanglement, that spooky connection where particles mirror each other instantaneously across any distance. Quantum computers exploit this phenomenon, using qubits that exist in multiple states at once to crack problems exponentially faster than classical machines. Now picture a wormhole linking two entangled particles. According to the ER EPR conjecture, that tunnel isn't just a bridge, it's the physical manifestation of their quantum link. In other words, the universe might be computing by threading information through spacetime's hidden shortcuts. The parallels run deeper. Just as qubits rely on superposition, existing in a blend of 0 and 1 until measured, a wormhole's throat could exist in a quantum flux, its geometry unresolved until something traverses it. Calculations that would take eons on a supercomputer might unfold near instantaneously through a wormhole's twisted topology, like solving an equation by folding the paper it's written on. The most complex cosmic puzzles, from simulating galaxy formation to modeling quantum fields, could be child's play for a spacetime-based processor. But here's the twist: if wormholes are nature's quantum computers, they might not just process information, they could store it. Black holes famously scramble data into apparent chaos, but wormholes might preserve it in their geometry, encoding answers in the way spacetime curves and stretches. The universe's entire history could be archived in a network of these tunnels, with each gravitational ripple or quantum fluctuation acting as a bit in the ultimate cosmic hard drive. The implications are staggering. Advanced civilizations wouldn't need to build quantum computers. They might tap into existing wormhole networks, harnessing spacetime itself as a computational substrate. Even more unsettling, if the cosmos is already computing with wormholes, we might be living inside its output, our reality the result of some unfathomable calculation unfolding across dimensions we can't perceive. Yet the wildest possibility isn't about technology, it's about origins. If wormholes compute, could they have played a role in the universe's birth? The Big Bang's initial conditions were improbably fine-tuned for life. Maybe that's no accident. Perhaps those conditions were the solution to a problem solved by primordial wormholes, a cosmic equation balancing itself in the first moments of existence. The universe might not just contain wormholes, it might owe its very existence to them. The human body was never designed for interstellar travel, but what if we rewrote the blueprint? Picture a future where evolution isn't left to chance, where genetic engineering and synthetic biology merge to create organisms capable of surviving the unimaginable stresses of wormhole transit. This isn't just about building better ships, it's about redesigning the travelers themselves. Take the humble tardigrade, Earth's most indestructible microanimal, capable of surviving the vacuum of space and lethal radiation. Now amplify those traits a millionfold. Scientists could engineer human cells with reinforced cytoskeletons to withstand tidal forces, or implant biomechanisms that trigger quantum state hibernation during transit. The blood might carry exotic matter analogs, stabilizing cellular structures against spacetime shear. These wouldn't be humans as we know them. They'd be post-biological pioneers, their very DNA threaded with wormhole survival protocols written in base pairs. But biological adaptation might not stop at genetics. Symbiotic nanotechnology could weave through tissues like cosmic scaffolding, repairing cellular damage in real time as the body endures wormhole traversal. Imagine trillions of microscopic machines coursing through veins, programmed to counteract gravitational distortions atom by atom. Some theorists propose even wilder solutions, replacing organic neurons with quantum-entangled networks that don't just survive wormhole chaos but thrive in it, turning the brain itself into a navigation system attuned to spacetime's wrinkles. The most radical vision, abandoning biology altogether. Advanced artificial intelligences, conscious digital entities housed in indestructible quantum substrates, might be the only beings capable of routinely traversing wormholes. Unshackled from fragile carbon-based forms, they could encode themselves into the very fabric of the tunnel, riding gravitational waves like surfers on a cosmic tide. Their perception of the journey wouldn't be the nausea-inducing whirl of human experience, but a fluid dance with multidimensional geometry. Yet even this pales next to the ultimate possibility: life forms born inside wormholes. Just as extremophiles thrive in Earth's harshest environments, certain theoretical models suggest self-replicating information patterns could emerge in the swirling energies of a stable wormhole throat. These wouldn't be creatures of flesh or silicon, but entities woven from spacetime itself, beings for whom traversal isn't a perilous voyage, but as natural as breathing. The implications rewrite the Fermi paradox. If the universe's most advanced life evolves beyond physical constraints, we might not recognize them as travelers at all. Their wormhole journeys could leave no detectable traces, their biology so alien it blends into the background of spacetime's architecture. The great filter might not be behind us. It could be waiting in the genetic codes and quantum matrices we'll need to master before the stars truly become ours. Plasma isn't just the stuff of stars and lightning. It might be the key to unlocking wormholes in a lab. Picture the fourth state of matter, where atoms are ripped apart into a seething soup of ions and electrons, responding wildly to magnetic fields and electric currents. Under extreme conditions, like those in fusion reactors or the hearts of stars, plasma can twist spacetime in ways that eerily resemble the physics of wormholes. The secret lies in its behavior. At temperatures exceeding millions of degrees and pressures beyond earthly scales, plasma creates self-organizing structures, filaments, vortices, and double layers that mirror the theoretical contours of a wormhole's throat. Take the Z machine at Sandia National Labs, where physicists compress plasma with magnetic fields so intense they briefly outshine the sun. In these experiments, the plasma's instability generates regions of negative energy density, exactly the exotic matter needed to prop open a wormhole, if only for nanoseconds. Similarly, inside tokamaks like ITER, the swirling plasma can form magnetic islands, pockets where field lines reconfigure into closed loops. These structures don't just trap particles, they warp local space-time in a way that mathematically echoes the Krasnikov tube, a hypothetical wormhole stabilized by circulating energy. But the most tantalizing parallels come from nature itself. Solar flares and coronal loops on the sun's surface exhibit plasma dynamics that look like fractal versions of wormhole geometries. When a flare's magnetic fields reconnect, they generate helical structures akin to a wormhole's twisted throat. Even more compelling, certain pulsars, rapidly spinning neutron stars shrouded in plasma, emit jets that behave as if funneled through an invisible tunnel, with particles accelerating to relativistic speeds without obvious cause. Could these be natural wormholes sculpted by plasma physics on a cosmic scale? The challenge is control. While plasma naturally mimics wormhole conditions, harnessing it demands precision beyond current tech. Stabilizing a plasma wormhole would require balancing unimaginable energies, like trying to tame a lightning bolt into a doorway, yet the payoff could redefine space travel. If we could encode a wormhole structure into a plasma's magnetic fields, we might not need exotic matter at all, just the raw, swirling power of a star bottled in a reactor. Some theorists push further, suggesting that advanced civilizations might already use plasma wormholes as transit networks. UFO sightings often describe craft enveloped in glowing plasma. Could that be the visual signature of a localized wormhole stabilization? The idea straddles the line between physics and speculation, but the math doesn't rule it out. Whether in a lab or a nebula, plasma's chaotic beauty might be hiding the universe's most elegant shortcuts if we learn to speak its electrified language. What if traversing a wormhole doesn't require a ship or a body, just a mind? This isn't just science fiction. Some theoretical physicists and consciousness researchers propose a staggering idea that wormholes might not be bridges for matter, but conduits for consciousness itself. Imagine a universe where the fabric of spacetime isn't just threaded with tunnels for physical travel, but with pathways for thought, where minds could leap across light years without moving an inch. The seeds of this idea lie in the quantum realm. Particles entangled across vast distances seem to communicate instantaneously, as if space doesn't exist for them. If, as the ER equals EPR conjecture suggests, entanglement is underpinned by microscopic wormholes, could consciousness, a phenomenon deeply tied to quantum processes in the brain, exploit these same connections? Experiments in quantum biology hint that photosynthesis and even bird migration rely on quantum coherence. Why not human thought dive deeper and the parallels grow stranger? Near-death experiences often describe tunnels of light, a common archetype across cultures. Traditional explanations point to oxygen deprivation or neural firing, but what if these visions are glimpses of something more? Could the brain, under extreme stress, momentarily tap into the universe's hidden wormhole network, perceiving the scaffolding of spacetime itself? Even dreams, with their nonsensical leaps across time and space, might reflect a subconscious interface with these cosmic shortcuts, stitching together realities our waking minds can't fathom. The math gets wilder. Certain interpretations of quantum mechanics, like von Neumann-Wigner consciousness causes collapse theory, suggest the observer plays a role in shaping reality. If consciousness interacts directly with the quantum foam, the seething foundation of spacetime, it might not just perceive wormholes but influence them. A trained mind could, in theory, stabilize or even summon a tunnel through focused intention, bending probability at the quantum level. Ancient meditation practices speak of transcending physical limits. Could these be accidental rediscoveries of a deeper, wormhole-linked potential? Yet the most radical implication isn't about individual minds, it's about collective consciousness. If thoughts can traverse wormholes, entire civilizations might communicate instantly across the cosmos, not with radios or lasers, but through shared mental space. UFO encounters often describe telepathic contact. Fringe theories suggest these could be encounters with beings who have mastered consciousness-based traversal, their minds flitting through spacetime's backdoors while their bodies remain light years away. Skeptics rightly point out the lack of hard evidence, but absence isn't disproof. Neuroscience is still unraveling how brains generate awareness, let alone how quantum processes might intertwine with cosmic geometry. Future experiments could test this. If meditators or psychedelic voyagers consistently describe similar wormhole-like geometries under controlled conditions, it might hint at a deeper connection. Or perhaps advanced brain scans will detect anomalies, quantum signatures in neural pathways that shouldn't exist unless entangled with something beyond the skull. Whether fact or fantasy, the idea reshapes our place in the cosmos. If consciousness and wormholes are linked, the universe isn't just a void to cross, it's a living network whispering to minds attuned to its rhythms. The greatest journeys might not need engines or exotic matter, but the quiet expansion of thought itself, reaching through spacetime's hidden, seems to touch what lies beyond. The universe might harbor its own fail-safe mechanism against self-destruction, wormholes acting as cosmic pressure valves, bleeding off the lethal energies of rogue singularities before they unravel reality itself. Picture a singularity spiraling out of control, its infinite density threatening to devour spacetime like a black hole gone rogue. Now imagine a wormhole forming at THE, Chinese letter, siphoning that destructive potential away like a lightning rod channeling a storm's fury into the ground. This isn't just theoretical fantasy, it's a tantalizing solution to one of cosmology's darkest riddles. How does the universe avoid eating itself alive? The math behind this idea emerges from the chaotic frontiers of quantum gravity. When singularities form, whether in collapsing stars or hypothetical vacuum decay events, they don't just bend spacetime, they strain it to breaking point. Some models suggest this strain could trigger spontaneous wormhole formation, like steam bursting a safety valve on an overheating boiler. The wormhole wouldn't just relieve pressure, it would redirect the singularity's lethal energies into alternate dimensions or distant cosmic voids, effectively diffusing the bomb. It's nature's ultimate contingency plan, written into the fabric of reality at the Planck scale. Evidence might already hide in plain sight. Gamma-ray bursts, the universe's most violent explosions, often exhibit energy signatures that defy conventional explanations. Some display sudden energy drops or anomalous afterglows, as if part of their fury was abruptly drained away. Could these be glimpses of nascent wormholes stabilizing just in time to prevent total annihilation? Even more compelling, certain supermassive black holes rotate at speeds that mystify physicists, their angular momentum curiously capped. A wormhole bleeding off excess spin could explain this cosmic speed limit, like an overflow drain in a cosmic bathtub. The implications rewrite our understanding of cosmic fate. If wormholes really do regulate singularities, the big crunch, the feared collapse of the universe, might not be inevitable. Each near catastrophe could spawn escape tunnels, redistributing dangerous densities across the multiverse. Advanced civilizations might even learn to engineer these safety valves, deliberately triggering controlled wormholes to stabilize dying stars or quarantine predatory singularities. The universe's longevity wouldn't be luck, it would be architecture, with wormholes as the hidden load-bearing walls keeping the cosmos from imploding under its own weight. Yet the most haunting possibility isn't about prevention, it's about purpose. If wormholes stabilize the universe, could they be part of a larger system, fine-tuned by some deeper physics or even an intelligence? The precision required suggests either an astonishingly self-regulating cosmos or something far more mysterious lurking in the equations we've yet to decipher. Either way, the next time a star collapses silently or a black hole spins just shy of critical, it might not be coincidence. It could be space-time itself exhaling through hidden doors, quietly ensuring the show goes on. What if the most practical wormholes aren't tunneling through space at all, but through lines of code? In simulated universes, whether hypothetical alien creations or advanced human virtual realities, wormholes could function as the ultimate optimization tool. Instead of painstakingly rendering every star in a galaxy or calculating every quantum fluctuation, a simulation might use space-time shortcuts as computational cheat codes, bridging distant regions instantly to save processing power. The concept flips our understanding of wormholes from cosmic phenomena to pure information architecture, where the tunnels aren't carved into the fabric of reality but woven into its underlying logic. Think of it like a video game streaming assets. When you traverse an open-world map, the system doesn't load every tree and mountain simultaneously. It prioritizes what's immediately visible. Now scale that up to a universe simulation handling trillions of planets. Wormholes could act as dynamic loading zones, linking far-flung sectors without requiring the simulation to process the intervening void. Need to simulate a star system 50,000 light-years away. Instead of calculating every atom in between, the system could stitch the destination directly to the observer's locale via a wormhole subroutine, rendering only what's necessary. It's cosmic LOD optimization taken to the extreme. This idea gains eerie traction when you examine glitches in our own universe. Quantum entanglement's instantaneous connections, where particles mirror each other across vast distances, could be the simulation's wormhole-driven data compression in action. Anomalies like dark energy's uniform pull or the universe's suspiciously even temperature might not be mysteries of physics, but artifacts of a system using wormholes to maintain equilibrium without overloading its processors. Even the speed of light, often seen as the universe's ultimate speed limit, might function as a rate limiter to prevent rendering errors in a simulation reliant on wormhole-based shortcuts. The most unsettling implication: if our reality is a simulation, its architects might have left traces in the wormhole math. Certain solutions in quantum gravity produce equations suspiciously resembling error correction protocols, as if the universe's code automatically repairs unstable wormholes to prevent crashes. The holographic principle, where our three-dimensional reality is projected from a two-dimensional boundary, could be a memory-saving measure, with wormholes acting as data pipelines between surface and volume. Even the apparent lack of visible wormholes might not mean they're absent, just that the simulation's rendering engine keeps them hidden in its back-end processes, visible only when it glitches. Yet the irony is delicious. If simulated universes use wormholes to function efficiently, their inhabitants, whether us or other civilizations, might eventually discover those same tunnels as physical phenomena. A super-advanced species could hack the simulation from within, repurposing its built-in shortcuts for their own travel. The ultimate cosmic rebellion wouldn't be breaking out of the simulation, it's hijacking its infrastructure, turning the system's own optimization tools into a backdoor for transcendence. Dark energy, the mysterious force accelerating the universe's expansion, might not just be pushing galaxies apart. It could be stretching spacetime so violently that it tears open wormholes, threading the cosmos with hidden tunnels even as it drives everything else to drift away. This counterintuitive idea turns dark energy from a cosmic antagonist into a potential architect, weaving shortcuts into the fabric of an ever-growing universe. Think of spacetime as a rubber sheet. Dark energy stretches it taut, making distant regions recede faster than light. But under extreme tension, materials don't just stretch, they crack. Wormholes could be those cracks, forming where spacetime's expansion outstrips its elasticity. Unlike black holes, which collapse under gravity, these tunnels might be forced open by the repulsive pressure of dark energy itself, like bubbles inflating in an accelerating loaf of bread. The math supports it. Certain solutions to Einstein's equations show that a universe dominated by dark energy could naturally generate wormholes, with the negative pressure counteracting gravitational collapse. The most startling implication: if dark energy creates wormholes, their distribution would mirror the universe's expansion. They'd cluster along cosmic voids, the vast, empty regions where dark energy's push is strongest. These tunnels wouldn't connect random points. They'd link regions destined to drift irrevocably apart, a cosmic subway system built to outpace the universe's accelerating disintegration. Civilizations of the far future, trapped by the growing voids between galaxies, might rely on these tunnels as their only escape from cosmic isolation. But there's a catch. These wormholes would be ephemeral, stretching and thinning as dark energy's grip tightens. A traveler stepping into one might find the exit receding faster than they could reach it, like running up an escalator speeding downward. To survive the journey, you'd need to move faster than dark energy's expansion, a feat requiring energies beyond anything we know. Yet advanced civilizations might exploit the tunnel's instability, riding the wave of expansion like surfers on a spacetime tsunami. The eerie twist: dark energy's value is unnaturally perfect for life, too strong and the universe rips apart before stars form, too weak and gravity crushes everything. But just right, and it might weave wormholes into the cosmic tapestry, as if the universe planned for its own expansion not to be a death sentence but a doorway. The fabric of reality might be far more interconnected than we ever imagined, not just a single universe, but an endless tapestry of parallel worlds, each vibrating at a different frequency, separated by membranes thinner than we can perceive. And wormholes, they could be the threads stitching these worlds together. This isn't just speculative fiction. Modern inflationary cosmology, The leading theory for the universe's rapid expansion after the Big Bang suggests that our cosmos might be one bubble among countless others in an ever-growing multiverse. Wormholes could be the bridges between these bubbles, hidden tunnels where the walls of reality grow thin enough to cross. Picture the multiverse like a cosmic loaf of rising bread, with each bubble universe a pocket of air in the dough. Inflation stretches the loaf, but where two bubbles press close, their boundaries might fuse not into a collapse but a tunnel. These wouldn't be the wormholes of Einstein-Rosen's equations, linking distant points in our universe. These would be interdimensional wormholes, threading through higher dimensions to connect realities with entirely different laws of physics. Step through one, and you might emerge in a universe where gravity is 10 times stronger, light moves at half speed, or time flows backward. The math behind this idea is as elegant as it is unsettling. Inflationary models predict that quantum fluctuations during the universe's first moments could have spawned an infinite fractal of bubble universes, each pinched off from the others as space expanded faster than light. But some solutions allow for these bubbles to remain tethered, not by shared spacetime but by quantum entanglement or higher dimensional geometry. Wormholes could be those tethers, cosmic umbilical cords never fully severed. String theory takes it further, suggesting that the multiverse's higher dimensions might naturally braid these tunnels into existence, like roots intertwining beneath a forest. Evidence might already exist in the cosmic microwave background, the afterglow of the Big Bang. Certain anomalies in its temperature patterns, like the infamous cold spot, could be scars from an ancient collision with another bubble universe. If such a collision occurred, it might have left behind more than just a bruise. It could have forged a wormhole, a relic passage between worlds. Even more tantalizing, some models propose that dark matter's mysterious behavior might stem from particles leaking into our universe through these tunnels, a slow drip from realities just beyond our grasp. But traversing an interdimensional wormhole wouldn't be like hopping between stars. The rules of physics could change mid-journey, unraveling atoms or rewriting the very concept of existence. In one universe, electromagnetism might dominate. In another, nuclear forces could be so weak that matter disintegrates instantly. The wormhole itself might act as a filter, stabilizing only certain configurations of matter or energy, a cosmic sieve ensuring only the compatible survive the trip. The implications rewrite the Fermi paradox. If civilizations can access the multiverse, they might not bother colonizing galaxies. They'd hop between universes, seeking ones with richer resources or kinder physics. UFOs could be interdimensional tourists, not extraterrestrials. Religious and mythological accounts of other worlds might be cultural memories of rare, natural wormhole openings, fleeting glimpses into realities beyond our own. Yet the most haunting possibility isn't about travel, it's about creation. Some theories suggest that traversing a multiverse wormhole could spawn a new universe, like a branch sprouting from a tree. Every act of passage might birth a fresh cosmos, its physics subtly altered by the journey. The multiverse could be growing not just from inflation, but from explorers like us, unknowingly planting new realities with every attempt to reach the next. What if the universe keeps souvenirs from its past lives? Wormholes might not just be tunnels through space, they could be cosmic heirlooms, relics from a time before the Big Bang. This radical idea suggests that when our universe was born, it inherited space-time shortcuts from whatever existed before, like a house with secret passages built by a previous owner. The math behind this comes from bouncing universe models, where each Big Bang is followed by a big crunch, cycling endlessly. In these models, wormholes could survive the collapse, threading through the death of one cosmos and the birth of the next, like stitches holding together the fabric of reality itself. Picture the final moments of a dying universe: black holes merging, galaxies evaporating, space-time itself unraveling. But wormholes, stabilized by exotic physics or higher dimensional geometry, might endure the chaos. As the next universe inflates from the ashes, these tunnels would stretch and warp, their mouths anchoring to new points in the fresh spacetime like roots regrowing after a forest fire. The result, a network of ancient shortcuts older than time as we know it, connecting regions of our cosmos that should have no business being linked. The evidence could be written in the sky. The cosmic microwave background, the afterglow of the Big Bang, shows puzzling anomalies like large-scale temperature variations that defy standard inflation theories. One explanation, these might be scars left by pre-Big Bang wormholes, their gravitational fingerprints baked into the universe's first light. Even dark matter's uneven distribution could hint at these relics, their mass warping the cosmos in ways that mimic invisible matter but actually trace back to structures older than existence itself. But here's the mind-bender: if wormholes predate our universe, their destinations might not just be elsewhere in space. They could lead to elsewhere in time. A tunnel forged before the Big Bang might exit into a realm where causality runs backward, or where the laws of physics are subtly different, like a bridge between two versions of reality. Traveling through one could be less like taking a shortcut and more like stepping into an ancestral memory, a place where the rules haven't just changed, they never applied to begin with. The most haunting implication: if wormholes are relics, they might not be accidental. Some theories suggest advanced civilizations in prior universes could have engineered them intentionally, leaving behind a roadmap for successor cosmoses. The tunnels could be messages in bottles cast into the chaos of a collapsing universe in hopes that someone, or something, in the next cycle would find them. We might not be the first to dream of crossing the stars. We might just be the latest to inherit the keys. Particle accelerators already push the boundaries of known physics, smashing atoms at nearly light speed to recreate conditions unseen since the Big Bang. But what if these collisions don't just produce new particles? What if they briefly puncture spacetime itself, birthing wormholes smaller than atoms yet profound enough to rewrite the rules of reality? This controversial idea stalks the edges of quantum gravity research, suggesting that the very machines built to uncover the universe's secrets might be tunneling through it all along. Take the Large Hadron Collider, the most powerful particle smasher ever built. When its proton beams collide, they concentrate energy so extreme that, for a split second, they mimic the seething chaos of the early cosmos. Under these conditions, some theories predict spacetime could undergo quantum foam-like fluctuations, forming microscopic wormholes that evaporate before anything can traverse them. It's like striking a match in a darkened room and catching a glimpse of a hidden door, one that vanishes before you can step through. The math fueling this speculation comes from string theory and loop quantum gravity, which allow for spacetime's fabric to become foamy at the tiniest scales. In these models, high-energy collisions could twist spacetime into knots, creating structures resembling Einstein-Rosen Bridges. The catch: these wormholes would be absurdly unstable, lasting perhaps a billionth of a trillionth of a second. Detecting them would require instruments sensitive enough to spot anomalies in the debris of collisions, patterns of particle scattering or energy, losses that hint at something stranger than a new particle, a fleeting tunnel through spacetime itself. Critics dismiss the idea as fantasy, pointing out that even if microscopic wormholes form, they'd collapse instantly under their own gravitational pull. But supporters counter with a wild possibility. Certain quantum gravity models suggest these tiny tunnels might not need exotic matter to stabilize. Instead, they could be held open by the collision's own energy, like a soap bubble expanding for just a moment before popping. If true, it would mean wormholes aren't just astrophysical curiosities, they could be laboratory phenomena, waiting for us to refine our tools enough to catch them in the act. The most tantalizing clue might already exist in unexplained data from past collider runs. In 2010, the LHC's CMS detector recorded anomalous events where particles seemed to vanish, their energy unaccounted for. Mainstream physics chalks this up to measurement errors or unknown particle decays, but could it be the fingerprint of a microscopic wormhole siphoning matter away? Even more provocative, certain quantum entanglement experiments show particles influencing each other faster than light could travel between them. If ER equals EPR holds, these spooky actions might be signatures of Planck-scale wormholes woven into the experiment's fabric. The implications electrify futurists. If we could create and stabilize even a single microscopic wormhole in a lab, scaling it up would become an engineering challenge rather than a physics impossibility. Imagine a future where colliders don't just discover particles, they stitch spacetime into networks, crafting interstellar gateways one atom-sized tunnel at a time. Of course, skeptics warn of hubris. The energies required might exceed anything achievable on Earth, or the wormholes might prove impossible to control, collapsing into black holes that devour the experiment and the experimenters. Yet history favors the bold. Every major leap in physics, from splitting the atom to confirming the Higgs boson, began as a fringe idea. Whether particle accelerators are unwitting wormhole factories or not, their collisions keep revealing a universe far stranger than we imagined. The next time protons collide at near light speed, who knows what doors might flicker open in the wreckage and what might be watching from the other side? Gravitational waves ripple through spacetime like echoes of cosmic violence, colliding black holes, merging neutron stars, the shuddering birth of new singularities. But what if some of those ripples aren't from collisions at all? What if they're the cosmic equivalent of footsteps, the tremor of something or someone passing through a wormhole? When LIGO first detected gravitational waves in 2015, it opened a new window on the universe. Now, physicists are tuning that window to listen for whispers of spacetime's hidden shortcuts. Here's why it's plausible. A traversable wormhole, by its very nature, warps spacetime dramatically. The moment something enters its throat, the gravitational field would oscillate, sending shockwaves through the fabric of reality. Unlike black hole mergers, which produce a characteristic chirp, as their frequencies rise, a wormhole traversal might generate a gravitational wave signature more like a dampened echo. Picture dropping a pebble into a pond, but instead of ripples spreading outward, they bounce back and forth between the wormhole's mouths before fading. That's the kind of anomaly LIGO successors could hunt for. The math behind this prediction is staggering. Simulations of wormhole dynamics show that their gravitational waves would carry two telltale quirks. First, the frequency wouldn't climb smoothly like a black hole merger's. It would oscillate unpredictably as the wormhole's throat stretches and recoils under the strain of passage. Second, the signal might include afterpulses, secondary waves caused by the wormhole's mouths vibrating like drumheads long after the initial event. These wouldn't match any known astrophysical process. If LIGO or future detectors like the Einstein telescope catch such a pattern, it could be the smoking gun for a traversable tunnel. But there's a catch. Natural wormholes, if they exist, are probably rare, and their gravitational waves would be faint compared to cataclysms like neutron star collisions. Detecting them would require instruments of almost unimaginable sensitivity. That's where LISA comes in. Scheduled for launch in the 2030s, this space-based gravitational wave observatory will probe frequencies too low for ground-based detectors, perfect for catching the deep, resonant hum of a massive wormhole's oscillations. It's like switching from listening for a mouse's footsteps to feeling the distant tread of an elephant. The most tantalizing possibility isn't passive detection, though, it's active probing. Some theorists propose sending targeted gravitational waves toward suspected wormhole locations like cosmic sonar. If a hidden tunnel exists, the returning echoes would carry distortions no ordinary object could produce. Advanced civilizations might already be doing this, their artificial gravity pulses flickering across the cosmos like lighthouses scanning for portals. For now, the hunt remains speculative. But with each new gravitational wave detection, we're not just mapping the universe's visible catastrophes, we're tuning our ears to the subtler murmurs of spacetime's secrets. And if we're lucky, one of those murmurs might just be the sound of a door creaking open. Black holes have long been cosmic paradoxes, regions where gravity triumphs so completely that not even light escapes. But what if their impenetrable event horizons aren't the end of the story? The infamous firewall paradox suggests that instead of a one-way ticket to oblivion, the edge of a black hole might be a seething wall of quantum fury, incinerating anything that crosses. Some physicists now propose a radical resolution. Those firewalls aren't destruction at all, they're the mouths of hidden wormholes, twisting information away to someplace new rather than erasing it forever. The puzzle starts with quantum mechanics' insistence that information can't truly vanish. Toss a book into a fire and its ashes still encode the original words, just in a scrambled form. But black holes seem to break this rule. As Stephen Hawking showed, they slowly evaporate via quantum radiation, leaving no trace of what fell in. This information loss contradicts quantum theory's bedrock principles, sparking decades of debate. Enter the firewall idea. In 2012, physicists Ahmed Olmary, Donald Maroff, Joe Pulczynski, and James Sully argued that preserving information requires the event horizon to become a blistering barrier, a firewall that vaporizes infalling matter before it reaches the singularity. The proposal sent shockwaves through physics. Firewalls violate Einstein's equivalence principle, which states free-falling observers shouldn't notice anything unusual at the horizon. It's like claiming the edge of a waterfall is suddenly molten lava when viewed up close. But wormholes offer an elegant escape. If the firewall isn't a destructive wall but a transformative threshold, a wormhole's entrance, then information isn't lost. It's rerouted. Imagine jumping into a black hole and encountering not a curtain of flames but a tunnel's mouth, its throat lined with quantum entanglement. The violent particle interactions we interpret as a firewall could actually be the birth pangs of a wormhole, scrambling information not into chaos but into a new state ready to emerge elsewhere. This reshapes the singularity itself. Instead of a crushing dead end, it might be a bridge, a Planck-scale wormhole throat connecting to another region of spacetime. The math hints at this. Certain solutions show black hole interiors can pinch off from our universe, forming separate spacetime bubbles linked only by microscopic tunnels. Information entering the black hole would teleport through this wormhole, encoded in Hawking radiation emitted on the other side. It's like burning a message but having the smoke reconstitute itself into the original text light years away. The implications rewrite cosmic bookkeeping. If every black hole birth spawns a wormhole, then the universe's darkest objects might be clandestine couriers, ferrying information through hidden channels. Colliding black holes wouldn't just merge, their wormhole networks might stitch together, creating labyrinthine connections between points we perceive as separate. Even the Big Bang singularity could be reinterpreted as a wormhole mouth, bridging our cosmos to a prior universe's collapse, yet mysteries linger. How does the wormhole stabilize without exotic matter? Why doesn't the infalling traveler perceive the tunnel? Some theories suggest quantum gravity effects dominate at the horizon, warping local spacetime so severely that the wormhole's formation is instantaneous from the outside but imperceptible within. Others propose the firewall wormhole duality is a cosmic sleight of hand, an illusion created by treating gravity and quantum mechanics separately when they're fundamentally entwined. Future experiments might settle the debate. Gravitational wave detectors could hunt for anomalies in black hole mergers, echoes, or frequency shifts, hinting at wormhole throats flickering into existence during the collision. Quantum computers simulating black hole dynamics might reveal information reappearing in unexpected ways, mimicking wormhole traversal. And if we ever decode Hawking radiation's fine structure, we might find signatures of scrambled messages slipping through spacetime's backdoor. The firewall paradox once threatened to unravel physics, but by reimagining flames as doorways, we might uncover a universe where nothing is ever truly lost, just hidden in plain sight, waiting for us to follow. General relativity gives us wormholes as cosmic shortcuts, while quantum mechanics governs the bizarre behavior of the smallest particles. But what happens when these two titans collide? Enter loop quantum gravity, a theory where spacetime isn't smooth and continuous, but woven from tiny, indivisible loops. In this pixelated cosmos, wormholes might not be anomalies. They could be inevitabilities stitched into reality's very fabric. Imagine spacetime as a tapestry. In Einstein's universe, it's a seamless sheet warped by mass and energy. But loop quantum gravity suggests it's more like chainmail, a mesh of interlocking loops so fine we've never noticed the gaps. At these scales, the distinction between inside and outside blurs. A wormhole here isn't a tunnel dug through spacetime. It's a natural knot where loops twist back on themselves, creating shortcuts through the quantum weave. The math reveals something astonishing. These loops can form braids that resemble microscopic wormholes, their stability guaranteed not by exotic matter, but by spacetime's own discrete geometry. This reshapes the stability problem entirely. Traditional wormholes rely on hypothetical negative energy to stay open, but loop quantum wormholes might stabilize through quantum spin networks, patterns of angular momentum that reinforce spacetime's structure like cosmic stitching. Picture a shoelace tied just right to hold its shape without glue. The loop's inherent spin could generate enough repulsive force to counteract collapse, making exotic matter unnecessary. The implications ripple across physics. Black hole singularities where general relativity breaks down might dissolve into wormhole-like structures under loop quantum gravity's rules. As matter approaches infinite density, the looping spacetime could bounce, funneling the collapsing star's remnants through a quantum tunnel to emerge elsewhere. This elegantly sidesteps the information paradox: no singularities, no lost data, just a cosmic rerouting via Planck-scale wormholes. String theory offers another quantum gravity perspective. Here, wormholes might arise from higher dimensional branes colliding or intersecting, their gravitational shadows manifesting as four-dimensional tunnels. Some models even suggest that entangled particles in string theory are connected by open strings stretching through extra dimensions, essentially quantum wormholes in disguise. The ER EPR conjecture bridges both theories, hinting that entanglement and wormholes are dual descriptions of the same phenomenon, seen through different mathematical lenses. Experimental evidence remains elusive, but subtle clues exist. Loop quantum gravity predicts spacetime's granularity should slightly delay high-energy photons traveling across the universe, an effect some argue is visible in gamma-ray bursts' arrival times. If confirmed, this granularity could indirectly support quantum wormholes, as both stem from spacetime's discrete nature. Meanwhile, tabletop quantum experiments are testing whether entanglement's properties align with wormhole dynamics, probing the theory's edge with lab-grown analogs. The dream, a unified framework where wormholes aren't exotic outliers but inevitable features of quantum spacetime bridges between relativity's cosmic heights and quantum mechanics' subatomic depths. Whether through loops, strings, or some deeper theory yet unseen, the answer may reveal that the universe's greatest shortcuts were hiding in plain sight all along, woven into the quantum code of reality itself. Imagine our universe not as a solitary existence, but as one of countless cosmic offspring, each birthed through a wormhole stretching from a dying reality into a newborn one. This radical vision redefines wormholes from mere shortcuts through space to something far grander: cosmic umbilical cords, linking parent universes to their children in an endless cycle of creation. The idea springs from cyclic cosmology, a model where universes don't just end in heat, death, or collapse, but regenerate through a process akin to biological reproduction. At the heart of this theory lies a stunning reversal of the black hole's role. Instead of devouring everything, a black hole's singularity might trigger a quantum bounce, a rebound so violent it births a new spacetime. But here's the twist: the bounce wouldn't just create a disconnected universe. A wormhole could form during this transition, threading through higher dimensions to tether the newborn cosmos to its predecessor. Picture a collapsing star not vanishing into oblivion, but squeezing through a space-time bottleneck, emerging as a big bang on the other side, a cosmic inheritance passed through the tunnel's throat. The math behind this is as elegant as it is mind-bending. Solutions to loop quantum gravity equations show that under extreme densities, repulsive quantum forces can halt a collapse and trigger an expansion. Pair this with string theory's brain's higher dimensional membranes that could collide to create universes, and wormholes become the natural conduits for this recycling of reality. It's like a cosmic game of telephone where the laws of physics whisper from one universe to the next through spacetime's hidden channels. Evidence might already lurk in our universe's first moments. The cosmic microwave background's eerie uniformity, the fact that distant regions have identical temperatures despite never being in contact, could hint at a wormhole's imprint. If our universe inflated from a tunnel connected to a prior one, that connection might have homogenized conditions before snapping, leaving behind telltale patterns in the primordial heat. Even dark energy's mysterious prevalence could be a relic of this birthing process, like stretch marks in spacetime from its violent passage into existence. But the most profound implication isn't about origins, it's about legacy. If wormholes are birth canals, then our universe might be teeming with nascent realities budding from its own black holes. Every collapsing star could be a potential parent, its singularity the seed of a new cosmos. Civilizations facing cosmic doom might not flee to other stars, they could cultivate black holes, guiding the birth of successor universes tailored to their survival. It's the ultimate act of cosmic gardening, planting the seeds of reality itself, yet the cycle raises haunting questions. Do physical laws mutate slightly with each iteration, explaining why our universe seems fine-tuned for life? Could a prior civilization's experiments have shaped our constants through some wormhole-based engineering? The answers might lie not in telescopes, but in the quantum murmurs of black holes at the edge of oblivion, where one universe's death rattle becomes another's first cry. From the shimmering possibility of quantum foam wormholes bubbling beneath reality's surface to the radical notion that dark matter itself might be a hidden web of spacetime tunnels, these 30 theories don't just push the boundaries of physics, they blast them wide open. Imagine a universe where black holes aren't dead ends but backdoors, where the Big Bang left behind cosmic shortcuts like breadcrumbs through time, where consciousness itself might surf through wormholes woven into the fabric of existence. Every neutron star could be hiding a gateway in its crushing heart. Every particle collision in our labs might birth fleeting tunnels smaller than atoms, and the very expansion of the cosmos could be tearing open doorways we've yet to recognize. The beauty of these ideas isn't just their audacity, it's how they force us to rethink the fundamentals. Gravity isn't just a force, it's space-time's sculptor, bending the universe into shapes we're only beginning to trace. Matter isn't just stuff, it's the raw material for bridges across dimensions. Even the emptiness of space isn't empty at all. It's a quantum froth seething with potential, where wormholes flicker in and out of existence like cosmic fireflies. Whether through the math of string theory, the echoes of gravitational waves, or the eerie patterns in our deepest telescopes, these theories whisper that the universe is far stranger, far more connected than we've dared to dream. Now it's your turn. Which of these ideas grips your imagination? Is it the haunting vision of white holes birthing new universes, or the spine-tingling possibility that UFOs might be tapping into a galactic wormhole network? Maybe the thought of our entire reality being a simulation optimized with spacetime shortcuts leaves you reeling. Drop your favorite theory in the comments. Let's geek out over the cosmos' wildest possibilities together. And if you love diving into the deep end of science, hit that subscribe button and ring the bell. There's so much more mind-bending stuff coming your way, and you won't want to miss where we go next. The universe is weird, wonderful, and waiting for us to explore. Let's keep unraveling its secrets one theory at a